So welcome to the second week of the course. In this week, you will be learning about the normal distribution, which is probably the most important data distribution that you're going to learn in the course. It is a part of the continuous distribution family, and today we will be discussing various calculations involved with the normal distribution, the shape of the distribution, and then some very important properties that will be the key to answering several questions in the later part of the course. Okay, so Professor Wan, let's start with what a normal distribution looks like.
Well, a normal distribution is bell-shaped, and it can represent many things in the real world, such as the height of people, blood pressure, etc. It is useful because there is a lot of applications in the real world. Being bell-shaped also means that it is symmetrical. There is the same area to the left and to the right of the mean. The total area under a normal distribution is 1. And it represents probability. So the values are between 0 and 1, equally distributed to either side of the mean. That means that either side has a 0.5 probability value. If you add the two, half of it is 1. The total area is 1. And like we were saying before, it is symmetrical. And within this symmetry, therefore, you can find a value either to the right or to the left or in between two particular z-score. What a z-score is, it represents the number of distributions that you are away from the mean. So let me take a break and see if Professor Katri has any questions or any additions.
Right. So one of the most important things about the normal distribution, I guess that we can see some examples here. Each curve that is colored represents a normal distribution. So for example, if we look at this dark blue curve, the first thing we'll notice is that it's very narrow. It's sort of narrower than the other curves that we have here. And looking at this key over here, we'll notice that it says n, which stands for the normal distribution. And then it has a 0 and then comma and then 0.2. This is a standard representation of the normal distribution. The first value here always represents the mean. The second value always represents the variance. So looking at the first curve here, that's dark blue, we can see that the mean is 0. Well, it's 0 for the red curve as well as this pink curve, and the value here is -2. So at least in the first three cases, the value is 0. And what that represents is that 0 is the central point of the distribution. Each of these three different curves are centered around 0, and we can see that is the case. So 0 is the mean, the median, as well as the mode. And 0.2 is the variance. Now compare that to the other variances. In the case of red curve, it's 1, and in this case, it's 5. So we can clearly see that among these three, 0.2 is the lowest value for the variance, which is why it's the narrowest. We know that from Module 1, when you have smaller variance, that means data is less variable. Now let's look at this third case where the variance is 5. Well, you can see how variable this distribution is, right? It's still centered around 0, but the data values are further apart. And looking at this last case where the mean is -2, What that means is that the data distribution is shifted to the left relative to all these other three curves. Just like Professor Wan said, the curve represents the distribution of values in a data set. And the area under the curve, so imagine if you were to highlight area under the curve, that would represent the probability. One of the most important rules in the topic of normal distribution is what we call the empirical rule. So, Professor Wan, what is the empirical rule?
The empirical rule tells you what is the area that we find under 1, 2, and 3 standard deviations to either side of the mean. If you notice, to the right is a positive value, to the left is expressed as a negative value, and the curve usually expands to plus or minus 3 standard deviation, because by the third standard deviation, pretty much the entire value of probability is so very close to 1 will be covered.
Right. So, in other words, if we had a normal distribution like this with the mean that's centered here, then we expect right about 68% of the values fall within 1 standard deviation of the mean. And 95% of the values fall within 2 standard deviations of the mean. And 99.7% of the values fall within 3 standard deviations of the mean. And essentially, so what we're doing is we're using standard deviation as a metric of how far away we are from the center. So in this case, for example, we are 1 standard deviation away from the center. In this case, we are now 2 standard deviations away from the center. In this case, we're 3 standard deviations away from the center. And so when we do different problems and examples, you will always be given the value for the mean and the standard deviation. And so you will be able to say that if you're 1 standard deviation away, so let's say the mean is 0 and the standard deviation is 1, then if you're 1 step away from the mean, then this area under the curve will be 0.34. If you are 2 steps away from the mean, then this area from the center all the way to 2 standard deviation will be 0.34 plus 0.135 and so on. So this is a very nice illustration in Zybook that I would like to use, and we'll see what the output here is. So a distribution that is unimodal and symmetric is centered around the mean, and standard deviation determines the spread of the distribution. Approximately 68% of the data is within 1 standard deviation from the mean. Notice it says within 1 standard deviation, and what that means is 1 to the right and 1 to the left. So together, it's about 68% of the data is within 1 standard deviation of the mean. Again, 95% of the data is within 2 standard deviations of the mean, and 99.7% of the data is within 3. Almost all of the data is within 3 standard deviations away. What that means is as you approach 3 standard deviations away from the mean, you tend to almost have very low probabilities after that. So before we start some examples on the normal distribution, where we will be calculating probability for given critical values of a normal distribution, and also calculating critical values when probabilities are given, I want to highlight these 2 calculators that are in Zybook. These calculators are going to be extremely important when you do these calculations, not only because, first of all, they give you the answers and you can match your answers with them, but also the fact that they will build a graph, highlight the appropriate areas under the curve, and it just helps to visualize the problem. Problems involving calculations in normal distributions are critical, and it is very important to first visualize what we are trying to solve, and then solve it and then verify it. So when we do these next few examples in Python, I will refer back to these calculators and show you that we get the same answers as Python outputs, and that we also get a graph that will help you visualize the problem. Let's now do some examples using Python functions. And in these examples, we will calculate probability for a normal distribution when the critical value and the direction is given. And also, we will calculate the critical value itself if the probability and the direction is given. We will start with importing the appropriate module or the submodule that will help us do these calculations. And in the case of the normal distribution, the functions that calculate these various scenarios they are included in the module called SciPy, and the submodule is scipy.stats. So I will first import this, and then we will now be able to do the various calculations. So here's the first example. For a normal distribution, if the mean is 55 and the standard deviation is 7.5, what is the probability that a given x value is less than or equal to 62? So our critical value is 62, and we are interested in probability that is less than that. So clearly, this is going to be the area that gets highlighted is going to be less than 62 on the left side of 62 all the way to the end of the distribution. When we are given the less than or equal to sign, we will use st.norm.cdf. .cdf is basically the method that we use whenever we have less than or equal to sign. The first value that goes in the function is the critical score or critical value itself, that's 62. The second value that's input is always the mean, and the third value that's input is always the standard deviation. So let's run this, and we get 0.8246. That's the probability of x less than or equal to 62 if the mean is 55 and the standard deviation is 7.5. Let's verify this using the calculator that's in Zybook. So my mean is 55. Standard deviation is 7.5. Less than or equal to 62. Let's build the graph. Here's the graph. Here's the area that gets highlighted, and the answer is 0.8247, which is the same answer here. Okay, so let's move on to the next example. For a normal distribution, if the mean is 55, standard deviation is 7.5, what is the probability that x is greater than or equal to 51? So now it's 51. 51 is on the left side of 55, and we are interested in the area that's on the right side of that critical value of 51. So the area that gets highlighted will be on the right side of 51. And what is the function, the Python function for this? Well, again, we're going to use st.norm because we're dealing with normal distribution, and the method to use here is called sf. So always use sf whenever you have the greater than or equal to case. So in this case, the first value again is the input. The first input is always the critical value. The second input is the mean. The third input is the standard deviation. So let's run this, and we get 0.7031. Let's now verify this in the calculator. So I'm using score of 51 and greater than, and here's the area that gets highlighted, and the answer is 0.7031. That matches this answer right here. Okay, let's now do a slightly more complex problem. For a normal distribution, if the mean is 55 and the standard deviation is 7.5, what is the probability that a given value of x falls between 49 and 60. So now we have two critical values, a lower value and an upper value. And we have to find the probability that a value happens to be between them. So when you, let's do this in Zybook calculator first, and then we'll come back here. So let's actually visualize this first. So 55, 7.5, 49, and 60. So for this case, I'm going to pick between, and you'll notice that automatically the calculator now has two inputs. So I'm going to put 49 here and 60 here and build the graph. And as you can see, now the area that gets highlighted is between those two critical values, and it is 0.5357. So how do we solve this in Python? There's no new function for this case. That's because we can use an existing function to solve this problem for us. How do we solve it? Well, we can use the CDF function that gives us the probability of less than. So we will first calculate probability that a given value is less than 60, the upper, that is the upper critical score. If we do that, we highlight all of this area, right? Less than 60. So that's what we get here. And then from that, we subtract the area that is to the left of 49, which is the lower critical value. And we're subtracting that. So if we put 49, we get this area. So if we subtract that other area that I had, 60 or less, and we subtract this from that, we will get area in the middle. And that is the trick that we're using here to use the CDF method to solve a problem. We call this the between problem. It's always between two critical values. So that's how we can solve that problem. Now, let's use the other scenario where we are given the probability and we have to get to the critical score, the critical value or the critical score. For a normal distribution, if the mean is 55 and the standard deviation is 7.5, what is x star if the probability that a given x is less than that x star, the critical value, is 0.8247? So how do we solve this? Notice that we have a less than sign, and because now we're going to use the probability to get to the critical score, we're going to use a method called PPF. Okay, and the input to the method is, the first input is the probability, the second is 55, which is the mean, and the third is the standard deviation, which is 7.5. Let's run this, and we see that we get 62. So 62 is this critical value, x star. Let's do this in Zybook calculator. So we're going to move to the other calculator that takes probability as input and gives us the z-score or the critical score. So the mean is 55, standard deviation 7.5, and we have a less than scenario and the probability is 0.8247. And we expect to get 62 as the answer. So here's the area that gets highlighted, and notice that I get the critical value as 62. All right, and then we'll do the last case, which is the greater than. Same distribution. What is probability that a given x is greater than a critical value or a critical score? The probability is 0.95. So now we're using greater than sign. So the area that gets highlighted is to the right of that critical value. So I'm going to use ISF method. First input again is the probability, second is the mean, third is the standard deviation. I'll run this and I get 42.66. And this is the answer I expect if I change this to greater than sign and I use probability of 0.95 here. And notice that this is the area that gets highlighted, and the critical score is 42.66. So to summarize, these are the functions that you should remember for calculations involving probability and the critical values when a normal distribution is given. This is something that you will be tested on in the quiz as well. That takes us to section 4.5, that is on students' t-distribution. So as we will see here, the student t-distribution looks to be quite similar to the normal distribution in that it is still a bell-shaped curve that is centered around some value, which is again the mean. But there are some differences. So Professor Wan, what is a student t-distribution and how does it differ from the normal distribution?
Okay, the main point to remember with the t-distribution is that when we're working with problems where the standard deviation is not known and the sample size is less than 30. So that is the key point to remember, the t-distribution versus the normal distribution.
Yes, so very good point. So essentially what this means is that students' t-distribution is very similar to the normal distribution, except if you are given a problem to solve and the problem involves a sample size that is small. So just like Professor Wan said, that a general rule is to use 30 as the threshold. So if the sample size is less than 30, or you're not given the population standard deviation. So the population standard deviation is unknown, so that you have to use the sample standard deviation as an estimate. Then you would use students' t-distribution as opposed to the normal distribution. So let's do some examples, and you'll see that the Python methods for students' t-distribution, they're very similar to the normal distribution. So just as long as you know which distribution you're using in different problems, you'll know exactly what functions to use. Let's now do some examples for students' t-distribution. So just like before, I will import the submodule scipy.stats. And here's the first problem. For a student's t-distribution, if the sample size is 25, mean is 55, and the standard deviation is 7.5, what is the probability that the given x is less than a critical value of 62? So as you can see, I'm just using an st.t instead of the norm. I'm now using t. That signifies that I'm using the student's t-distribution. And the method name is the same as what we had before for the case of less than, when we were calculating the probability, CDF. So this CDF, the method names here, all of these different method names will be the same as what you had before, except now we're using the method called t, which again signifies student's t-distribution, as opposed to norm, which signifies the normal distribution. So in this case, notice that the sample size given is 25. And even though we're assuming here that we are given the population standard deviation, the sample size is small, right? It's less than that critical value of 30. So we're going to use students' t-distribution instead of the normal distribution to do these calculations. Previously, when we did the normal distribution, we sort of assumed that we had either had a very large sample or that we were considering the actual population of the data. So in this case, we're using t. So let's now run this. Here's the answer that we get. One important thing to note here is that because the sample size is 25, and just like Professor Wan mentioned, that the degrees of freedom that we have to calculate in each problem involving students' t-distribution, the degrees of freedom is always sample size minus 1. Okay, so in this case, it will be 25 minus 1. It'll be 24. And 24 is an input now to this method, t.cdf. So 24 which is the degrees of freedom, is the second input. The first input, just like before, is the critical score. The second is the degrees of freedom. Third is the mean, and then the last input is the standard deviation. Okay, let's look at this example. Same parameters. Mean is 55, standard deviation is 7.5, but the sample size is small at 25. Now we need probability that a given x or a given value is greater than the critical value of 51. So now we're considering greater than sign, and we're going to use SF for this case, and we're using T again for students' T distribution. And just like before in the previous example, we're going to use 24 as the degrees of freedom. So we run this, we get the answer as 0.70. The same trick can be used here to calculate the probability that a given x is between two critical values, a lower and an upper value. This is the same case here. Again, we're using T dot CDF to be able to do this, and the second input again is 24, and I should change this to 24. So when we run this, I get 0.5285. Now in this example, we are trying to calculate the critical value given that, and we are given the probability. So, and the sample size again is 25, mean is 55, standard deviation is 7.5. And again, we notice that the sample size is small. Therefore, we will use students' T distribution. And the question is, what is X star? What is the critical value if for a probability when X is less than that critical value is 0.8247? So we will use PPF method. And notice I'm again using T.PPF, and I get the answer there. And then for a student's T distribution, if the sample size is 25, mean is 55, standard deviation is 7.5, what is the critical value if the probability that a given x is greater than that critical value is 0.95? And so we will now use T.ISF. And again, we're using 24 as an input. We run this and we get the answer. So in general, what you will notice is that the method names are the same, except that in the case of students' T distribution, there's an extra input, which is the degrees of freedom. It's always calculated as the sample size value minus 1. So if your sample size is 100, degrees of freedom is 99. In this case, is 25. So the degrees of freedom is 24. And the rest of the values are the same as what goes in the methods for normal distribution. Let's now switch to the discussion for this week. And the discussion is on the central limit theorem. So in this discussion, again, just like the previous week, you will first go to this discussion forum. I highly recommend that you read the problem statement. It's also useful to read these questions just to get an idea of what is being asked. And then you will open the Python script for this discussion, and you'll run the script and you'll get your outputs, and you will be able to answer each of these questions here. This is a little bit of a comprehensive discussion this week, so I highly recommend that you start much earlier in the week. So in this discussion, you will apply the central limit theorem and use principles of the normal distribution to calculate probabilities. So there are two key parts of the central limit theorem. The distribution of sample means is approximately normally distributed. As the sample size increases and we repeatedly draw these samples, regardless of the shape of the population distribution from which the samples are drawn. So let me just briefly summarize this. Imagine you have a population and you're trying to study the population. So there's some metric that you want to study. Maybe you want to calculate the average income of that population. The population is large, so clearly there are not enough resources to study the entire population. So what we do is we pick out a sample. We take that sample, we calculate the sample mean, which we then say that it is the best representation of the population average income. What this says here is that the distribution of sample means is approximately normal as the sample size increases. And we repeatedly draw these samples. So just like the example I gave you that you pick out one sample from the population, now imagine that you pick out many samples and you keep picking these samples and you keep calculating your average income for that sample. So let's say I pick 1,000 samples. And so now I have 1,000 sample means. If I were to plot the distribution of those sample means, it would always be normal. And it would even be normal if the actual population distribution is not normal. Distribution where I'm picking from, if it tends to be skewed, the distribution of sample means will always be normal. We will demonstrate that. The second point is that the average of all sample means is equal to the population mean. In practice, the average of all sample means will closely approximate the population mean. So what does this mean? What this means is, remember I drew 1,000 samples from the population, so I have 1,000 sample means. If I calculate an average of those 1,000 sample means, that average will be very, very close to the unknown population mean that you're trying to look for. And that is the key and almost a very beautiful aspect of this theorem. And we will demonstrate both of these points in this discussion. So you will go to the Python code, you will generate your population data within the Python code. It will be automatically generated for you. However, and by the way, the distribution of that data will be skewed, so we will see that. Please be aware that the data set that you're going to use is unique to each student. So all of you will have different answers. So you will not be able to sort of just copy someone else's answer, because the data set that is generated for you is going to be unique to you. So please be aware of that as you answer the questions. And we will run step 1 in the Python script to generate our unique data. So let's go to the Python script. And I will click on Module 2 discussion. So here's the central limit theorem. Just like before, please be sure to read these different steps. Make sure you read the instructions here. So here's the data set that we're going to, step 1. In step 1, we're going to generate the population data that we are using. So let's do that. So here's the data set that came up. So there are a total of 500 observations. Now let's go to the next question. In your initial post, address the following items. So in the Python script, you created a histogram for the data set generated in step 1. Check to make sure this distribution is skewed. See step 2 in the Python script. So we should go to step 2 now. So in step 2, I'm creating a histogram plot of the population data. So let's click. So here's the population data. So Professor Wan, what do you think of this population data distribution? Is this skewed? And if it is skewed, which way is the skew?
It is definitely a skew. As you can see, it's not a symmetrical distribution. It's not normal.
Okay, so that answers the question here. In the Python script, we create the histogram. Check to make sure that the distribution is skewed. And yes, it is skewed. And by the way, by skew, we mean that that the distribution tends to have some outliers. You can see there are some outliers here. Most of the values are concentrated here, and due to these outliers in the right tail, the data distribution is skewed. So that answers this question. We move to the next one. What is the mean of the population data that was generated here? See step 3. So step 3 will calculate the population mean. Recall that in step 1 we generated the population data. In step 2 we visualized the population data, and in step 3 we will calculate the mean of that data set. So let's calculate the mean, and the mean is 489.3. Okay, so the mean of the data that we generated is 489.3. That is the population mean. So this is usually unknown. This is what we're trying to estimate using samples. So let's assume for now that this is an unknown population mean, and we know that it's going to be 489. Let's go to the next step. In the Python script, you selected a random sample with replacement of size 50. Note that this is a sufficiently large sample. What is the mean of your random sample? So in the next step, we will draw a random sample from the population that you generated in step 1. This block of code will select a random sample of 50 data points from that population data set that you generated, and then it will calculate the mean of that sample. So let's do that. So here's the first estimate. The sample mean comes out to be 427. So what happened here is that it randomly picked 50 data points from the population data set, and then it calculated its mean, and it came out to be 427.22. And each time I run this, I will get a different sample, hence I will get a different sample mean. You only need to run this once. And you can see that 427 is not that close to the unknown population mean of 489. And that is what we expect. Each time you generate a sample, sometimes it will come out to be closer to the population mean. Sometimes the sample mean will be not that close, like in this case. So that answers this question. Now, in the next step, what we will do is we will generate 1,000 random samples of size 50. So we will repeat the step that we just did, but 1,000 times. Then we will store all of the 1,000 sample means into a data frame. So let's go to the next step. So again, repeatedly drawing samples and saving sample means for each sample. So we're going to repeat the previous step 1,000 times, and each time we will save the sample mean. So we will have 1,000 sample means at the end. So here's the data frame of 1,000 sample means. So each time it generates a sample, calculates the mean. So these are the different means. Now let's go to the next question. So now that we just generated 1,000 random samples and we saved the sample mean for each of those 1,000 samples, so we have 1,000 sample means. The next question says, review the plotted data distribution for these 1,000 sample means here. Does this approximate a normal distribution? So we will go to the next step, step 6. By the way, it references the step here. And in this step, we will generate a visual, a histogram of 1,000 sample means that we just generated. So Professor Juan, do you expect this to be normally distributed or not?
The answer is yes, based on the characteristics of the center limit theorem.
That is correct. So we expect it to be normally distributed. So let's run this part of code. And here's the distribution of 1,000 sample means, and take a look at that. It's approximately normal. And compare this to the population distribution. So the population distribution was skewed. We generated 1,000 random samples. Each time we calculated the sample mean, and the distribution of 1,000 sample means is approximately normal. So the answer to this is that yes, it does approximate a normal distribution, and it confirms the first part of the central limit theorem. Let's read that again. The distribution of sample means is approximately normally distributed as the sample size increases and we repeatedly draw these samples, regardless of the shape of the population distribution from which the samples are drawn. So regardless of the shape. So we saw that the population distribution was skewed. We repeatedly drew samples from that population. So we had 1,000 samples. Our sample size was large enough. Notice that each time we were picking a random sample of 50, and the distribution of sample means is approximately normal. So it confirms the first part. Now let's go to the last question here for the initial post. What is the grand mean and the standard deviation of these 1,000 sample means? So we're calling the grand mean as the mean of 1,000 sample means. So we have 1,000 sample means. We just calculate the mean of those 1,000 sample means. And that's the grand mean. And what is the standard deviation? So if we go back. So this calculates that. So we will run this. And this time the grand mean, which is the mean of 1,000 sample means, is 489. Standard deviation is 45. Now, notice 489 is the grand mean. That's the mean of the 1,000 means. So let's see how that approximates to the population mean that was unknown. Notice the unknown population mean for the data set that you generated in step 1 was 489.3. So this was the unknown. This is something that you have to estimate. And when we calculated the grand mean, which is the mean of the 1,000 means, that comes out to be 489.95. Notice how well it approximates the unknown population mean. So the question here says, does the grand mean closely approximate the mean of the original distribution? Does this confirm the second part of the central limit theorem? So yes, it does approximate the mean of the original population distribution. And it does confirm the second part of the theorem, which says that average of all sample means is equal to the population mean. In practice, the average of all sample means will closely approximate the population mean. So we have just proven the two major parts of the central limit theorem. And this discussion walks you through it. This is what the central limit theorem is. It's best explained by an example like this. And I encourage you to also go online and read about the central limit theorem. Zybooks also has a section on it. So this is your initial post, and then you will be posting at least 2 response posts to other students. So the questions are, is their population distribution skewed? And if, well, it should be skewed for each student. And then, is their distribution of 1,000 sample means approximately normal? Yes, it should be. Does this confirm the first part? It should. Does their grand mean closely approximate their population mean? It should. Notice that it will not always be equal. It will be close enough. And if it's close enough, it's a good approximation. And it will confirm the second part of the theorem. And then the third question is, what have you learned about it? So in general, please make sure to read these instructions. Make sure to run the code step by step. And also, a very important note here is, once you have generated your population data in step 1 and you're solving all these other steps, please don't go back and change the population data. Because if you do that and you don't run the following steps, then the answers that you have in the following steps will correspond to the previous population data that you had generated. If you're going to change the population data by running step 1 again, please run all other steps. And again, a reminder, that this data set is unique to each student, so your answers will be unique. But for all these different scenarios that students will get for this population data, the theorem, the central limit theorem, will always hold. So that concludes this video for Module 2. So Professor Wan, is there anything else that we should discuss?
Well, thank you so much, Professor Kadri, for a beautiful example. And let me remind all the students to please contact your own instructor and look at the additional resources posted in each of the websites. If you have any questions after you look at the video, your local instructor should be able to help you. And otherwise, we look forward to working with you again next week. Have a good week.
Sounds good. See you all next week.